Hello everyone, my name is Olivia Nabawanda from Makerere University, Uganda, and I'll be giving a talk on distinct flattened partitions, avoiding a pattern of length 4. This is joint work with Taufik Mansour and Mark Shattuck. I'll begin with a few definitions, first one being a set partition. So supposing we have a set partition of this form where you have elements of a set. For example, in this case, we have elements 1, 2, 3 up to 9, but these elements have been grouped into different blocks in such a way that in each block, the elements are written increasingly and the blocks are arranged in increasing order of their first entries, as you can see in this form. So this is a set partition. Now, what happens when you remove the separators of these blocks and then the commas in each of the blocks, so that in each block the elements are written as sequences? So we end up with a structure of this form, and this is what we call a flattened partition. It's also worth noting that different set partitions may give rise to the same flattened partition under flattening. So this flattening operation is not unique. So in our case, in this work, we are interested in the distinct flattened partitions that result out of flattening a set partition. And we are denoting Pn to be the set of all distinct flattened partitions over n. And for example, when n equals to 4, we have 5 of them. And pattern avoidance. We say that a flattened partition pi contains a pattern tau if in pi we can find a subsequence that is order isomorphic to tau. Otherwise, we say that pi avoids tau. For example, in this flattened partition here, we can see that it contains the pattern 2, 4, 1, 3 because of the subsequence 9, 4, 6, 7, which is order isomorphic to 2, 4, 1, 3. So we shall let Pn of tau denote the set of all distinct flattened partitions that avoid a pattern tau, and we shall let small pn of tau denote the cardinality of this set. And what we mainly focus on in this work are the patterns of length 4, and we want to determine the counting sequence, small pn of tau, classify patterns by Wolff equivalence, and explain the appearance of Catalan numbers and their binomial transform. In fact, in this work, we mostly focus on the patterns that lead to the Catalan numbers and the binomial transform of these Catalan numbers. That is what we mainly focus on. In the earlier works, Callan 2009 initiated the study of pattern avoidance in flattened set partitions and classified all patterns of length 3. Liu and Zhang in 2015 extended Callan's study to several patterns of length 4 in flattened set partitions. Nabawanda and Dr. Rajao in 2021 shifted the focus to distinct flattened partitions and determined small pn of tau for all patterns tau in S3. These are patterns of length 3 on distinct flattened partitions. And in this work, we focus on patterns of length 4, and in particular, on the patterns that lead us to the Catalan number sequence, Cn-1, and the patterns that lead us to the binomial transform of the Catalan numbers, which we come up with this as their recursion. How do we prove these results? We begin, first of all, with the avoidance class using some statistics. And then with these statistics, we construct or we derive recursive relations. And then from these recursive relations, which also act as our functional equations, we use the functional equations now to find the generating functions using the kernel method. And mostly the statistics that we use to refine our avoidance classes are the last letter, second letter, last two letters, and other statistics related to descents and runs. And through this approach, we are able to naturally end up with the Catalan generating functions and the binomial transforms of Catalan numbers. I'll use just a representative case, and that is the 2413 avoiding flattened partitions. So let UN denote the number of all 2413 avoiding flattened partitions of length n. And I'll let, introducing in our statistic, I'll let UNI denote the number of all 2413 avoiding flattened partitions having the last letter as I. And the key idea is to refine this count by the last letter as our statistic. And this gives enough information to decompose a 2413 avoiding flattened partition recursively. So all 2413 avoiding flattened partitions have a form like this, where if n is not at the end, then it is somewhere and to act as the largest letter, and the letter that follows immediately after n will act as the descent bottom. And therefore, a 2413 avoiding flattened partition has this form. Alpha n j beta I, where j and I are subsequences in pi with length greater than or equal to 2 and less or equal to n. How does the decomposition work? So for any pi, which is 2413 avoiding, ending in I, we distinguish two cases. The first case is where n is the penultimate letter, meaning it's at the end, and therefore deleting this n and reordering the rest of the entries leads to a smaller object, which is counted by un-1 I. How about a case where n is not penultimate? That means we shall write our pi in this form. And now here is where the decomposition comes in. You realize that we can decompose our pi into two subwords or subsequences, which are themselves 2413 avoiding after standardizing. And this here tries to explain how the standardization works. And what would those two subwords be? The first one would be alpha n, and then the other j beta I, depending on how you want to decompose. But the main idea is that these two subsequences are themselves 2413 avoiding. And so that leads us to our recurrence relation using the last letter as our auxiliary statistic. And the recursion is that for I greater or equal to 3 and less or equal to n-1, we have UNI satisfying this recurrence relation. In fact, the double summation here, as you can see, depends on J and M, where J has to cater for all the possible choices of the splitting, while M is the parameter for the size of the sub-sequences. And the first term in our recursion is the one coming from case 1, where you delete the largest element n from the permutation, while the second term here is the one which comes by splitting the 2413 flattened partition into these two subwords. And this recursion is subject to these initial values. Now, from the recursion UNI, we can now define a distribution polynomial in Y, which we define as this, and then a bivariate generating function, which we call U of xy as the summation over n of UNY x to power n. And now solving or expanding this translates into an expression, as you can see here, which we solve to give the solution or the refined form of our bivariate generating function uxy as this. So this is the form. So how do we end up with the Catalan numbers? So we set y equals 1 in the bivariate generating function, and we end up with a polynomial expression of this form, which we realize can be written in terms of the Catalan generating function, which is given by the summation Cn x to power n, where Cn denotes now the Catalan numbers for the different values of n. And so from this expression here, we realize that C of x therefore satisfies this expression, and extracting out the coefficients gives us our 2413, avoiding flattened partitions, satisfying the expression Cn minus 1 for n greater or equal to 1. A second phenomenon where we have the binomial transform of the Catalan numbers. This works for patterns as listed here. And for these patterns, we use the same refinement philosophy as in the previous case of 2413. And we end up with generating with a recurrence relation. Though in this case, realize that something new happens. Instead of the classical Catalan sequence, where we have Catalan sequence square, where I have square root of 1 minus 4x, the solution now involves this under the square root sign. And this signals that the enumeration now is no longer governed by the Catalan numbers. And so solving the functional equation gives the generating function this, as seen here, and extracting out the coefficients of this generating function gives our numbers Pn of tau, where tau is any of these three patterns. And that is precisely, this is precisely the binomial transform of the Catalan sequence. So these three patterns form a different Wolff equivalence class. So the same strategy works across the different classifications of those patterns, giving us the Catalan number Cn minus 1, and the three patterns giving us the binomial transform of the Catalan numbers. And the main statistics that we use to refine are mostly the last letter, second letter, last two letters, and for the pattern 2143, we have the initial form 1, I, 2. All such flattened partitions have this initial form. And so the proof changes from pattern to pattern, but this is the main guiding principle is the same. We choose a statistic that makes the avoidance condition recursively possible. Now, we also observed something interesting, and that is the fact that for some patterns of length 3 and some patterns of length 4, they were giving rise to the same resulting sequence. So we decided to come up with a proof for those patterns which of length 3 and those of length 4, which have the same counting sequence. And we observed that for example, pattern 213 and 312 of length 3 had the same counting sequence, that is a power of 2. And also these two patterns of length 4 had the same sequence. And we observed that for all those patterns of length 3 which don't start with 1, when you insert a 1 at the beginning of each and then reordering the rest of the elements to get these patterns of length 4, the counting sequence will always remain the same. So this also led us to more Wolf equivalence classifications. And therefore, at the moment, this is what we have. We have these 7 patterns giving us the Catalan number Cn-1, these 3 patterns giving us the binomial transform of the Catalan numbers, and we have other patterns which were giving us different sequences, but still for each of these, the idea was the same. Look for a statistic that would give a nice recursive structure that you would use to define a recursion, and then using that recursion to find the corresponding generating function. We also observed that these two patterns, 2431 and 3241, had the same resulting sequence, and we tested these for n up to 15. So the question now remains open to construct a bijection between these two classes, these two sets of pattern avoiding flattened partition.